Hello everyone, let me start with the explanation of the lecture. Let me share my screen. Okay, so this is the question, the example question that we did not completely solve in the class. So let us look at it. Now, the question as this is the question already given and you have already started working on it, so I'll not go into further details. It just says that the angular, given this configuration, you have been given the value of alpha and omega and this configuration, and you have to find the angular acceleration of links BC and CD. Remember, it's the angular acceleration, which is the alpha BC and alpha CD, and also the linear accelerations of the points E, F, and G. Okay, so just for the sake of completeness and for certain tips and tricks, I've added the angles here. So FBC angle is 22.67, and the angle opposite to that is 35.32. Similarly, DCG is 48.63 and the angle opposite to that is 24.17. So the first step in order to finish the acceleration calculations, we have to start with the velocity diagram. Okay. So the easiest thing for us to do is to find the velocity of B with respect to A, because omega of AB is already given in the question as 10.5 radians per second. And we also know the length of the link AB. Okay, so that gives us a value of 525 millimeters per second. So what we do with this value is that we draw a line which is perpendicular to AB, which is like this. So velocity of B with respect to A is basically this line, and we know the direction the arrow is pointing towards the second quadrant. The arrow is such that this vector looks to be in the second quadrant because we know that omega is in this direction. So the velocity vector will be pointing in the direction of this omega vector, the tangential velocity. Okay, so don't confuse with alpha direction. So when you're finding velocity diagrams, the direction of the velocity vector, velocity of B with respect to A, you have to take into account the direction of omega, not alpha. Similarly, for acceleration diagrams, you have to take into account the direction of alpha and not omega. So once that is clear, we draw this diagram over here. From a starting point AD, we know the magnitude as well as the direction. We just draw a line perpendicular to AB with a magnitude of 525 millimeters per second. Okay. So now for velocity of c with respect to b, now we have already located point B, right? Because we know the magnitude and the direction. Now, we can find c with respect to b because c with respect to b is a vector which passes through B, and we have already located the point B. And it is perpendicular to the link BC. So this is the link BC, it's going to be perpendicular to that. So with that information, we just draw this dotted line. We don't know on which side C will lie. It can be on the top or the bottom. We just draw a dotted line. And we also draw another velocity, which is velocity of c with respect to d, because we already have located the d point. And VCDE, v velocity of c with respect to d, is a vector which passes through d, and we already know have located d. And it will also be perpendicular. Okay. And we know this vector is perpendicular to this link length CD. So we draw this line perpendicular. Again, we don't know we don't know the direction as well as the magnitude, but we just know the sense that it's going to be along this dotted line. Now these two intersect at a common point, and that point is now known as C. Okay, so we have now located this point. Now the velocity diagram is over. Now, if you are doing this in SolidWorks, okay, if you're actually doing this in SolidWorks, it's actually very easy to do because you can find the magnitude and directions in a single go. So this is a velocity diagram. Again, we have done it in SolidWorks. Now we have to find velocity positions F and G. Okay, so so what we can do is that we can write this expression where V can be found using the velocity ratio theorem. Okay, so this is the velocity ratio theorem. VE with respect to B. So E with respect to B divided by c with respect to. Remember, in order to do the ratio, we ensure that the vectors are all pointing in the same direction. The vectors used in the velocity ratios are pointing in the same direction. So if we are doing a velocity of E with respect to B, we have to do velocity of c with respect to B, so which means both these vectors are pointing in this direction. That's what we have done. Velocity of E with respect to B divided by velocity of C with respect to B is equal to EV divided by BC. So once we do that, it comes to 0.61 of VCB, velocity of C with respect to B. So we have already seen velocity of C with respect to B. It is 0.61 times the vector. So E will be somewhere over here. Let me zoom in on that. Okay, so that is done. Now comes how to find velocity of F. That's a little bit more involved. It's not just a simple velocity ratio. So for that, what we do is that we find the velocity of G with respect to C. So velocity of yeah, we can first do it with the G and then we can do it with F. Okay. So velocity of G with respect to C. Let's see here's velocity G. So velocity of G with respect to C will be perpendicular to this line GC. Okay, and is passing through the point C. So we already know point C is perpendicular to this and passing through point C. We don't know the magnitude yet. And at the same time, velocity of G with respect to D can also be located. It's going to be perpendicular to this line, GD, and passing through D. So we know D, we draw this perpendicular line GC, and wherever they meet, that is my point G. Similarly, we can do the same thing for a point F. Okay. In fact, we have done it here. Velocity of F with respect to C is a vector passing through point C and perpendicular to CF, which is this vector. And vector passing through point B and perpendicular to BF is basically perpendicular to the BF link is basically this, the meet of the point, and that is F. Now the fun fact is actually here. The fun fact is actually here. The reason why we drew this angle over here, so I'll just take this entire thing and paste it here. So see, once you have drawn the diagram, an easy way to verify the diagram is by matching these angles. So let's try to match these angles over here. So it's seen that the angles are same. So let's try to find that out. So we know that the angle CBF is 22.67. So in this case, it's going to be CBF. So this angle has to be 22.67. Let's come here. So CBF is basically this angle. Let's see if it holds true. See, 22.67. Perfect. So if one of these angles is the same, there's no need of checking the other angle, but we'll check it anyway. So similarly, BCF angle is 35.32. So BCF, this opposite angle, 35.32. See, 35.32. Perfect. Similarly, this will also match for this part. So GCA, let's look at the angle. GCA, 48.6. Okay. So GCA, see, this is 48.6. So perfect. And the other one also matches. So that's why I drew the angles, because it's a good way to also verify your answers. So I've completely drawn the velocity diagram. Now we come to the acceleration diagram. Now in this acceleration diagram, we try to find the tangential acceleration vectors. So again, starting with the known values, the acceleration of b with respect to a is alpha ab. Again, alpha is given in the question times ab link. So alpha times ab. Okay, so this has got angular acceleration as well as omega. So if it just had omega and no angular acceleration, then the alpha AB would have been 0, and there wouldn't have been any tangential component. There wouldn't have been any tangential component. But since AB link has got both omega as well as alpha, it will have two components of velocity, which is tangential coming from the alpha, and radial or centripetal, which is coming from the velocity vector or the tangential velocity VB with respect to A. So B with respect to, we've already figured this out, right, from the velocity diagram. So that's square divided by the link AB length. So that gives us some value. Okay. So the way we draw this is perpendicular to AB, as we have said. So we draw this AB a line length of 1.3 perpendicular to AB. So we have the AB vector which is perpendicular to AB. So like this. Okay, it's given in green vector. So this is the radial first and the tangential. So I've actually started with the radial first and then the tangential. You can do it either ways. You can also start with tangential first and then do the radial. So let's also look at the radial component. It's 5.5 meters per second square. It is parallel to AB and located towards A, or pointing towards A. It's parallel to AB. So it's AB, it's parallel to that. So this line is parallel to the line AB and is pointing towards A. So the purpose for doing that is that from my starting point, it is pointing downwards in the third quadrant. So I'll do the same. So I'll draw a vector which is pointing in the third quadrant. See, from B to A, it is located. So the A point with respect to B is located in the third quadrant. So I'll just use this pointing towards A just to give the physical location of this vector. So it will be the like this pointing towards A. See, A is here. So this is also A is here. Okay, so this becomes your radial vector. And from here we draw a line perpendicular to the radial vector, and we measure off 1.3 meters per second square over there. Now we don't know in which direction. An easy way to find out is 1.3 will be in this direction because this is the direction of alpha. Alpha is rotating in a clockwise sense. So this will also be in the direction of the alpha. So over here. So this is also over here. So these two dotted lines, the radial and the tangential, will give me the solid green line. The solid green line is my total vector of acceleration of B with respect to A. So similarly, we do the same activity for a C with respect to B. It's slightly different, so it's given in red over here. So for that, we first do the radial. So over here, you can see the radial C with respect to B. Again, B point is located, so it's easy to do C with respect to B because it's a vector which is passing through B. Okay, so again, we find the radial. In the radial part, it is pointing towards B. So the B is in this direction, in the direction of my mouse, which is towards the left. So again, I'll do it towards the left. Okay, so this is my C with respect to B radial, and the magnitude is 1.75. It's parallel to BC, so both the magnitude and direction is known. So once it ends, we draw a line perpendicular. Okay, we draw a line perpendicular over here, and we don't know exactly where they will, on which side it is. Okay, so we just let it be. We just draw a line perpendicular over here and just let it be. So we have done until this red colored vector. Now we are remaining with this black colored vector. So the black colored vector is nothing but the acceleration of C with respect to D. Again, we know the radial component because we have figured out the tangential velocity of C with respect to D. So the radial component of A of C with respect to D is nothing but tangential component whole square divided by CD. And this is given as 2.86 meters per second square. Now remember that this 2.86 meters per second square is actually 2860 millimeter per second square. So you have to multiply this with 1000. So 28600 millimeters per second square, and there's a scaling factor involved over here in the acceleration diagram. Okay. So just remember that. So all these things which are drawn on SolidWorks are drawn with the scaling factor. Okay. So we know the direction is parallel to CD. So basically it's parallel to CD and it's pointing towards D, which means it's, so from wherever we are starting this acceleration C with respect to D, it is going to be pointing downwards. So we started from here. C with respect to D is passing through D. So from here, it is basically pointing downwards with this given magnitude and parallel to CD. So we know the direction, we know the magnitude, so we can mark off this line over here. This is nothing but mark off this point. So it is acceleration of C with respect to D, the radial component, and we draw a line, this dotted black line, perpendicular to this component. Okay, and we don't know on which side it will lie, but fortunately this black dotted line, the tangential component of this black vector and the tangential component of this red vector will meet somewhere or intersect somewhere. That is the point C. So once we figure out point C, we can draw the solid lines, basically the solid red line, the solid black line, And the solid black line represents A of C with respect to D, the total vector. And the solid red line represents A of C with respect to B, total vector. Okay. So now once we have that nailed down, now we can try to solve for the angular accelerations of link CD and BC. Okay. Now where we get this value, so A of C with respect to D, A of C with respect to is basically this solid vector line. And this we know we can measure it from SolidWorks, and it comes out to be 5.18 meters per second square. And AC with respect to D tangential. So CD, the tangential part, is basically this line. So we can again measure that off from SolidWorks too. So this is basically the tangential line. Okay, and we can see it is 432.67. So this is with this is the scale down value. So it's 432.47 times 10. So it is 4326.7, or rather 4.32 meters per second square. Now, in order to find the alpha of CD, which is basically this, the angular acceleration of this link BC, angular acceleration of this link CD, we can use this vector formula where alpha CD tangential is equal to, A linear acceleration ACD tangential is equal to alpha CD cross R of C with respect to D. So these are my vectors. So the only unknown here is alpha CD. So let us assume that alpha CD is given by alpha, this is the magnitude, and in the positive sense of my z-axis, the rotation is in the positive sense about my z-axis, which is K. Okay, and R of C with respect to D is something which you can find from the configuration diagram. See, it says it's confined from configuration diagram. So this C with respect to D, if you measure this angle, this comes out to be 79.65 degrees. So it's a vector, right? So, and it's in the second quadrant. So in the second quadrant, my I is negative and my J is positive. So minus cos 79.65 plus sine 79.65 J. This is my vector definition, and this is my magnitude of the vector CD. It's already given 56, right? So this is your simplified values over here. And this is, there's no scaling factor used in R, right? So this is the way it is. And from the diagram, we can find the magnitude of acceleration C with respect to D. The tangential is already found out over here. Okay. And as you can see, acceleration C with respect to D is a vector. Now, if you draw a coordinate system at the tail of this vector, so the tail of this vector is at here, and the head of the vector is pointing here. Okay, so we draw the coordinate system at the tail, and you see this angle. It's 10.36 with respect to these horizontal lines, which means this is a vector which is lying in the third quadrant. Now remember, in the third quadrant, both my I and the J components are negative. Keep that in mind. This is what we have done. So this is minus cos and minus sine. Both of them are negative, and the value is 10.35 degrees. So once you have that, you have this vector sorted out. Okay, you have this position vector sorted out. The only unknown is from the CD. So you write out this expression. You accumulate all the I terms and accumulate all the J terms. So in that way, you can have just two equations, one in I and one in J. And you've got two equations and one unknown, but if you solve either of them, you should get the same exact value. Yes. But it does not matter if you had assumed over here alpha CD to be like minus alpha CDK. It does not matter how you assume it, because in this case, if you had assumed it to be minus, the final answer would have been minus. Okay, so it does not really matter. And so you have this alpha CD sorted out. Now you can find alpha C with respect to B, which is this one. Okay, you can get the magnitudes again from the acceleration diagram made over SolidWorks, or in your case on a piece of paper. So again, we do the same treatment as we have done. The tangential acceleration is equal to alpha cross R. Now you can see here, this is the tangential component of the acceleration of C with respect to B. This is the tangential part, and this is 217.71 millimeters in SolidWorks. So it's scaled down by a factor of 10. So the actual value will be 2177.1. Okay, so 2177.1 is nothing but 2.17 meters per second square. You divide by 1000. Okay, so you do the same treatment. You find out the position vector of r of c with respect to b. So r of c with respect to b, the head is at c, the tail is at b. So you draw a coordinate system at the tail, and you find that this is a vector which is pointing in the first quadrant, which is lying in the first quadrant. This angle is 10.29 degrees. The first quadrant, both the I and the j and are positive. So cos 10.29 and plus sine 10.29. So you do the same treatment again, you get two equations from I and j, and both of them will give you the same value of 77.26. Okay, so that's the easy part. A little bit tricky over here is finding out the linear accelerations of f point and g point. Linear acceleration of E is actually simple because you see E is lying on this link BC. Okay, it's already lying on that link BC. So we know that E will also lie on the vector diagram of BC. So this is the acceleration diagram. Okay, we can use the ratio, the ratio theorem, which says that A of E with respect to B divided by A of C with respect to B. Again, we have to be consistent here. So A of E with respect to B is basically a vector pointing towards E starting from B. Okay, in the same way, in this ratio, C with respect to B is also vector pointing towards C. You see the sense of the direction of these two vectors are the same. This is very important. Is equal to the ratio EB divided by CA. And once you work out the math, you can see that A of E with respect to B is 0.6 times A of C with respect to B. So it is more than 50%. So you can locate point E over there. Okay, so that takes care of E. And you can actually measure E with respect to B, this measurement from SolidWorks. And don't forget to multiply it by the factor of 10, which is your scaling factor. Alternatively, you can also find E with respect to a fixed point, which is A or D. So acceleration of E with respect to A is actually, acceleration of E with respect to is actually this line. Okay, it is actually this dotted line over here. So that value from SolidWorks will be 520.51 millimeters. Remember, SolidWorks will only give you in millimeters or length. You have to multiply that with 10 to 5200.51 millimeters per second square. So you can also find that. Now we can also find these values from SolidWorks. Again, remember that this is the velocity diagram, so we have not used any scale for the velocity diagram. Yeah, so we are there. There's no scaling for velocity diagram, so you just write down these values. See, I'm trying to find G and F points, so my velocities that I require are G with respect to C, G with respect to D, F with respect to B, F with respect to C. You can measure all of the magnitudes of these values from the diagram on your piece of paper. Now we can again say that the acceleration of F with respect to B, the tangential, is alpha BC, or F with respect to B. And again, let me copy this figure again and put it over here. Okay, so the angular acceleration of BC we have found out. So this entire triangle BCF rotates as a single unit. So BC angular acceleration can be used for the angular acceleration of BF also. Okay, so tangential part, you can find it like this. And for the radial part, you can find it VFC squared divided by FC. And these are all the values. We have also tabulated them in a chart below. You can see it's the tangential part over here and the radial part. Just letting you know, it's the radial part only that we need. Okay. The tangential part is kind of like optional. Okay. This part is actually optional. Radial part is something, again, which we need. This tangential part is optional. I mean, if you find it out, I mean, no issues. You can always verify your answer. So we only need to find the radial parts, radial components, because we know the direction. Okay. For the tangential ones, we do not know the direction. The radial part, we know the direction as well as the magnitude. So let's see F with respect to B. See F with respect to B, the radial part is 119. it is 1.19 meters per second square, which is 1190 millimeters per second square. Now in SolidWorks, you have scaled it down by a factor of 10, so it is 119.36. So we draw that it is parallel to FB. So parallel to FB, basically it's parallel to this line FB, and its magnitude is this much. So we can draw the, and then it's pointing to the left side of its starting point. Why? Because F with respect to B is pointing towards B. So this is pointing in this direction. Okay. So we mark that off, and from here we draw a dotted perpendicular line because this is the tangential component direction, but we don't know the magnitude. We can do the same thing for F with respect to C radial. See, this is F with respect to C radial. We have been able to find the magnitude. Again, we draw a perpendicular line for the tangential part, and wherever they meet or wherever they intersect, that is my F. Okay? That is my F point. So that's pretty simple. And again, we can verify this value. So this A of F with respect to C tangential, A of F with respect to C tangential is coming out to be 0.99 meters per second square. So 0.99 means 990 millimeters per second square. Okay, 990. Yeah, and once we put it in SolidWorks, it should be 99 millimeters on SolidWorks. So this line should be 99 millimeters on SolidWorks. You should also do a quick check just to verify your answer. Okay. So this is nothing but I've just drawn the link CB separately or BC separately, because if I keep on drawing everything on top of this diagram, it becomes a mess. That's why I've drawn this separately. So CB is nothing but this line. Okay. And also, fun fact is the reason we have drawn these angles. Okay. The reason we have drawn these angles. Now, if you measure this angle, which is FCB, and if you go back over here, original diagram, FCB. So FCB in this configuration diagram is 35.32. This FCB should also be equal to 35.32. Okay. So this is a rain check, or this is a sanity check, or this is a verification of a method. And the same thing which we can do for a G, for finding the G point. Again, this is AD and this is C. So instead of drawing the full-blown acceleration diagram, so I've just drawn this line over here. This is C, this is AD. So I've just drawn this line, which is this line. And we do the same analysis. We know the radial components, so we'll figure out the radial components over here. So this is the radial component 122, corresponding to this, again, scale down. And this is the radial component G with respect to D. So this is around 225, so it's 225, again, scale down. And from here, we draw the perpendicular tangential line. For this one, we draw the perpendicular tangential line. Wherever they intersect is my point G. Again, a good way to check for sanity is if you go here and measure GCA or GCD, it should be the same as GCD. So see, GCD is 48.63. GCD, this should also be 48.63. Okay, and this other angle should also match with the angle in the configuration diagram. This is a good way to check for your answer, and that's it. I mean, you can also use that information in other different ways, this angular similarity information. Okay, so that's it. So I missed out in class to show you how to locate point G. So as well as point F. So this is the answer. Now, this length over here is nothing but your acceleration of G with respect to D. Okay, so D is a fixed point. D is a fixed point. So that's it. You have found the acceleration of G with respect to a fixed point just by measuring this. This is the magnitude, and the direction is basically a vector which is pointing in the third quadrant. Similarly, this is F. So this is acceleration of F with respect to B. It'll be somewhere over here, acceleration of F with respect to B. Now, if you want to find F with respect to a fixed point, which is A or D, you can just join that line. Okay, and that magnitude of that line is nothing but your acceleration of f with respect to a fixed point, say a. Okay? And the direction is whatever is the direction. That's it. Okay, thank you for paying attention, and all the best for your exam.